Today we're talking about columns, and you know what columns are? Those are the nice vertical elements that we have in our buildings. These are some nice pictures of columns. The columns are usually a vertical structural member supporting axial compressive loads. Those loads that come from the top floor and from the floor being supported. Normally they have compressive loads with or without moments, and we said that the cross-sectional or dimension of the column is generally considerably less than its height, which means you will see something that has as far as a ratio of the height to the width. You have a big height and you have a small width of the column, and they support vertical loads from floors and roof, and then transmit them down to foundation. So the main thing we have as a criteria is safety, and we want to safely take the load from higher floors down to the foundation. Now, there are mainly two types of column reinforcement. Those nice vertical ones, we call them longitudinal reinforcement. And those that are tying them together, they're called transverse or secondary reinforcement, and those are of two types, either ties or spirals, where the ties are the ones that just come and tie up like rings. You have rings taking the shape of the column, whatever the shape of the column is, and those spirals are normally, they come as one nice spiral shape, and they just keep spiraling or circulating around the column to tie it down. Now the tied and spiral columns, we said the 95% of the columns in buildings are tied. You very rarely see this shape. And the core of the spiral is more restrained because of the continuity of the nature of continuity of spiral that goes around the column. And this increases the load capacity. And we also said that spiral does not really work for, not very practical for rectangular and square columns. They're more practical for circular columns. And those tied are more practical for any shape. They can take any shape that we want. So normally buildings are coming in the shape of squares and rectangles. So in this case, tied columns are the most used ones. Now, as far as compressive strength, we will consider that all the columns, for the purposes of this chapter, are short columns. When I say short columns, it means that they will never exhibit buckling. So I will never have this problem in a column, right? Now this here, now we consider this a cylinder column or long column. When the aspect ratio of the height to the cross section of the column is very high, it will be subject to having this problem, which is the buckling problem. But for now, we will just consider looking at short columns. So the reason why we call them short is not because they're short, it's because they will not exhibit buckling. So column cylinderness does not need to be considered. They will not buckle. Failure depends on material properties and cross-section geometry only. Now, for the sake of calculations, we will think of a reinforced column as a column that has two components. Those two components are concrete and steel. So the area of the concrete will be AC, the area of the steel is AS or AST, and the total area is both of them combined together, called area gross. And then the stress taken in the steel is Fs, taken in the concrete is Fc. Now, if we put this together in equilibrium, that P, part of it goes to the steel and the other part goes to the concrete. This is the concrete part, this is the steel part, ACFC and ASTFS. Very simple and very straightforward. The area times the stress plus the area times the stress. Whatever comes from the concrete, whatever comes from the steel. And based on this fact, we will back calculate our capacity of the column. Now, for ductile failure, we must assure that steel reinforcement will yield before column crushes, right? And at that time, we have a strain in the steel equals to 0.002, which is F yield over epsilon steel, while that 0.002 corresponds to the maximum stress of the concrete, while the crushing of the concrete happens at 0.003. So we will consider that what happens to whatever strain, because this is one of the assumptions we had early on in the course, we said whatever the strain we have in the steel will be the same strain we have in the concrete, because we will assume that they are very homogeneous, they work together. You compress, both of them will deflect exactly together, even though steel is much stronger. The steel ratio, one of the very important components we have, is how much steel do I put in the column? So the ACI code has limitations for a column to be called a column, for a reinforced column. What are those limitations? Very important. It is between 1% and 8%. Now you cannot put reinforcement in a column less than 1%. If you put less than 1%, it will be under reinforced. Your steel will be very critical. It might not even work. And if you put more than 8%, it will not be practical. It will be very congested. It will be very hard to pour concrete in it. You will impossibly do any lap splices. So you will have to use some mechanical couplers or welding, but kind of groove butt welding of reinforcement to avoid having that double reinforcement ratio at lap splices. So practically speaking, the maximum ratio I can use is 4%. Why is this? Because of the lap splice. Let's think about this. If I have a column coming from the bottom, and this is my floor, and then I will continue this column later on after I cast my concrete. So normally where we stop casting is somewhere here. So this here is the lower floor column. That here goes to the next floor. So where do we stop? So somewhere here. This is where we stop so that we can pour our concrete for our reinforced slab, right? Where is the reinforcement of the concrete? It comes this way, and somewhere it stops. It must stop. I would consider this as just a break line. So now that reinforcement of the steel of the column will have to be developed somewhere in the upper column, and then another steel cage of the upper column will come and lap with it for a certain distance. When we go to the chapter of detailing, this distance will be the lap splice distance, LDS. I have to lap splice them and wrap them together so they can transmit the force from the upper floor to the lower floor. Now, if I put a reinforcement ratio here, now let's look at the section of this column. It will look something like this that has some reinforcement. Right? Let's just consider this as a 4 reinforcing bars column. Now, at the time of the lab, every bar, now this here will be the second section, every bar will have another bar next to it. Correct? So in this case, my 8% will become 16% at the lap splice. So this violates the code. If the code tells you it's only 8% limited reinforcement ratio, that means if I'm going to lap splice, I cannot put more than 4%. And the reason for that is my lap splice region will have the 8%. And even though with having the 4%, the 4% is considered very high, is considered very uneconomic. So in my opinion, if we're going to choose a good reinforcing ratio for regular buildings, let's try to shoot for a row that is between 1 and 2%. Okay? A 1 to 2% is a very good ratio for buildings. The lower, the better. Go 1.3, 1.5, that would be a very good ratio. If you believe it goes much higher than this and you require more than this, then start thinking about alternatives. And alternatives of this is having a bigger column or increasing your F prime C right? This happens a lot, that you specify an F prime C for columns that is different than F prime C for slabs, because columns are considered heavy loaded members, okay? And then if we substitute area concrete, remember that area concrete is actually area gross minus area steel in the equation that we had before, then it's FC times area gross minus area steel plus FC area steel. And now we considered that the failure will always happen at 85% of F prime C. Remember this fact that we've been using in all the bending. Now we just substitute the FC with F prime C. And we considered that the yielding will happen at the same time at the crushing or reaching the maximum stress. So we will consider F yield had happened as well. Why are we considering both happening at the same time? Because we said the two curves, this guy here goes at around 0.002, right? And we considered that this guy reaches the maximum at 0.002. So if both of them reached it at the same time, then we can simply consider F yield happened exactly at 0.85 F prime C. And then we can have this nice equation for the column capacity that will just wait for some more factor of safeties to add. What are those safety factors? We have two types of safety factors that are added to the column. The first one is the phi factor. And then the phi factor is very simple for columns since they're only subjected to compression. Remember, we had 0.65 for a compression controlled beam. It was 0.65. And then when it goes to tension controlled beams, it used to be 0.9. In this case, it is a pure compression column. So it is compression controlled member. We use 0.65. But then they found that spiral columns, they behave much better than tied columns. So for spiral columns, they said we can use phi, my phi factor equals 0.75. So if it's tied columns, 0.65. If it's spiral column, 0.75. And then there is another factor here that we have. What is this factor? Those are made for accidental moments. What is accidental moment is we have columns will never have pure axial. They will always have something that is applied from the side. For example, you're the last column, definitely you have some moment. You have a bigger moment from one side than the other side, you will have accidental moment. You have a beam that is not centered with the column, you have accidental moment. And in this case, those reasons, unbalanced moment, misalignments, or any loading type of inequality between sides will cause this. And the reason for having those, the 0.8 and the 0.85, is what we call the accidental moment. Any moment that is unaccounted for in the design. As you said, the interaction diagram is my next step. Now I'm having this nice axially pure axial moment. We will just compare our PU. This is the applied load. This is applied load, right? Applied, factored, or ultimate load. We will compare it to phi PN, right? Either it is spiral or it is tied. I will compare it to phi PN. And then if PU is less than or equal phi PN, then you are safe. I think this is the basic concept we know about columns. Everybody agrees with this. Now, what if I have moments? Well, I have actual moments, which means I have PU and I have MU. In this case, they developed something to account for both loadings together, which is PU and MU. So we developed, or people developed, structural engineer developed interaction diagrams. Let's look together what interaction diagrams are. Now, those interaction diagrams are a diagram or a graph that is drawn between moments on the horizontal axis and axial on the vertical axis. And they said this is the backbone. So if I come here and I draw the interaction diagram, and I consider now, if I'm purely applying axial load, so this is Pn. Forget the phi. Let's forget the phi for now. Let's just look at nominal, axial nominal moment. And this is nominal moment. When I say the word nominal, that means it is the load or the moment my member will fail at. So if I get this column, let's not draw it here. If I get this column and I have it subjected to only moment, just pure moment, it will fail at this Mn. Everybody agrees with this. It's just a purely calculating what is my Mn. Remember what my Mn is? It's C or T multiplied by the distance d minus a over 2. Very simple, straightforward. If I have this column subjected to pure axial, so no moment, it will fail here. Everybody also agrees with this. How we calculated this? The same equation we just looked at in the last slide. Now, they started to load this column with a combination of P and N. So somewhere here, I have some P and I have some M. This is M and this is P. So they found that the relationship at the time they are failing goes like this. It does not go as a straight line. It does not go as a nice curve. It just has a weird pattern, which is this pattern here. So at the time you're applying this P and this M, this P and this M, they will fail at that point. So at the time I have both together simultaneously, meaning at the same time, I have P and M, I will have limitations by this nice backbone curve. Okay, then in this case, if I have my PU and MU, this is my PU and this is my MU, giving me a point that is falling inside my interaction diagram, it will be safe. If my PU, let's put it in a different color, make the purple. If my PU and MU, see, on purpose I made it less. MU here and PU here. This fill outside the interaction diagram, it is unsafe. You got the idea? Even though PU by itself is less than the maximum. And MN by itself is less than the maximum. But both together are falling, or making a point that is falling outside. So anytime my interaction diagram points fall inside the curve, within the curve, it is safe. This is the safe area. Anytime it falls outside the curve, it is unsafe. Very simple, straightforward solution. People have already did a lot of work to draw these interaction diagram for us. There are now computer programs that you guys will be exposed to within this course to practice, which is SP column, or which used to be PCA column. It generates the interaction diagram for you in moments, just a few seconds. You generate it. If the points is inside, you're safe. If the points are outside, you're unsafe. But this interaction diagram is very interesting, and we need to understand why it takes this weird shape. There is a weird shape here. Why would an interaction diagram look like this? So the reason for such a change in the direction of the interaction diagram is because this area at the beginning is the tension controlled area. So the more axial load you place on the column, the less of tension in the strains you have, and you will be able to take more moment. Until one point, which is the balance failure, where both tension and compression failures happen at the same time, concrete crushes at the same time, tension steel yields, and then afterwards you go up to the compression controlled zone. So I have one point where I will have zero tension and fully under compression, and then thereof I will have just pure tension, pure compression applied. And that's the reason why my interaction diagram will look like this. The reason for this is at a pure moment, I get my nominal moment with a tension controlled behavior. The more axial I put, I'll be able to put more moment until I reach balance, and then I go back. So looking for the strength reduction factor phi, since we were talking about before, we said 0.65 for tight columns, 0.75 for spiral columns. That's if it's under pure axial. Now what if it's subjected to high moments that ended up making it tension controlled? It will be just like the regular tension controlled phi between 0.65 and 0.9. Now if it's pure compression controlled, it will be the 0.65 and 0.75 we talked about. So it is exactly the same as our bending, flexural design. But if it's proven to be more compression controlled, more towards the pure axial, it's 0.65, 0.75. If it's proven to be more towards the moment side, the higher moment, less axial, it will be more towards the 0.9 phi factor. Let's take an example, 10.1. Calculate the maximum axial load capacity of the tight column shown in the figure below. Now this column has 8 bars. I have 8, 5, 29. It has an area gross equals to 400 times 400. And then it's subjected to axial load only. So I will just use the phi Pn equation. In this case, I will, since it is tight columns, I can simply tell it's a tight column, it's not spiral. My phi factor is 0.65. I use this equation right away. My area steel equals 2 times 4, that's 8 times 529, that gives 5,160. I plug this inside the equation here and here, right? My F yield is 420, and my area gross is 400 by 400. And since it is tied, I have 0.8. And then get this equals 3522 kilonewton, which means if I put 35, 30, it will be unsafe. 3523, it will be unsafe. Now it will not fail because we have some safety factors here, but what we have as nominal times my phi is my limit for this column. Now for interaction diagrams, they were able to produce non-dimensional interaction diagrams. What do you mean by this? It means that I don't really have to draw a specific interaction diagram for every column. I can do a more general one that fits all types of columns, all dimensions of columns. That's why we call it non-dimensional. It is useful to express this way of interaction diagram for independently, that is independent from the column dimension. It is done by dividing the phi Pn by area gross F prime C and dividing the phi Mn by the area gross H times F prime C as well. So this becomes my dimensionless interaction diagram. What I mean by this, it means that this interaction diagram, I would consider each one of these as a different interaction diagram. The difference between them is the amount of steel inside. And so if I have a column that is H by B, I will have it, whatever the size is, those will be changed. And then instead of having Pn and Mn, I will have Kn and Rn, where Kn equals to Pn over F prime C area gross, and Mn equals Mu or Mn, Rn equals Mn divided by F prime C area gross H. Why do we divide by H as well? Because we want it to be unitless, where the H is in the direction of the moment. So my moment is in the direction of H. That H down here is the H that goes alongside with the moment. Now this is for a column that looks like this in reinforcement, where my reinforcement is distributed on all sides. Now, if the distribution of the moment is different from one column to another, I have to go to a different interaction diagram. So for example, if I have it only at the sides, those are a lot of times for frames, for example, you have very heavy reinforcement on two sides and light reinforcement or no reinforcement on the two other sides. In this case, we use this interaction diagram. And then for a circular column, we have a different type of interaction diagram. So before I decide which interaction diagram, I have to see which column and how it looks like to decide which types of interaction diagrams to go with. Before we proceed, what is within this interaction diagram? We said that this is Kn, this is Rn. That's the shape of the column. My Mn is expressed in terms of Pn times E. Why is this? So in case I don't have moment, but I only have eccentricity, I can simply say my moment is produced due to eccentricity E times the Pn. So it is the same thing, which means over here, this value is Mn, and this value is Mu. Okay, so we need to understand this. Second, my rho, if I have less reinforcement, I go here. This is 1%. More reinforcement all the way to 8%, I go here. So each one has its own reinforcement. Now, what if I have a 5.5%? Then I have to go here and imagine an imaginary line that goes exactly in the middle between the 5 and the 6. In this case, this will produce my rho equals 5.5%. So for any time I'm looking for the exact line, I can interpolate roughly where the line is for the specified steel reinforcement ratio. Okay? Now my next is also looking at my E over H. What is E over H? E is my eccentricity and H is this distance, my column width in the moment direction. Now those lines are the lines for my E over H. So having E over H equals 1, that means you're outside here at a distance equals H. Having E over H equals half, which is this one, that means my load is exactly at the edge. Having E over H equals 0.1, that's very small. Having E over H equals 0, that means you have pure axial load. So you'll be here. So this line is the line for E over H equals 0. Simple. Why do we need to look into this? So we can relate the eccentricity to my location of axial load, right? At the time you're outside the column will be different than you're inside the column. You can determine how far you are with your loading in terms of where your column section is. Another one is it also tells you what your Fs equals as far F yield, right? Because we remember that all the way down here, your Fs will be equal to F yield. You go up here, your Fs becomes less than F yield, so you know you're compression controlled. So down here, you're tension controlled. Up here, you're compression controlled. This point is the balance point. Okay? What difference does it make? It makes difference in the phi factor. Because the phi down here becomes 0.9. The phi up here goes less all the way until it's 0.65. Or 0.75 depending on whether it's spiral or tie. Okay? So we understand a few things by looking on where we are in the interaction diagram. Okay? The last item or the last component we wanted to explain is gamma. You see gamma, you will see different gammas for different columns or different interaction diagrams. What gamma is the ratio of where your steel is. Here's my steel. The ratio of where your steel is to how big my column is. Because different people might have different concrete covers, might have different rebar dimensions, right? Rebar fee. And then in this case, this will make a difference in how it resists. So the bigger the distance between the bars, the stronger the column, right? Because you have bigger arm. So this is H. If this is H and this here is, for example, we call it X, then your gamma equals X divided by H. What is X? Center to center of the rebars. What is H? The whole width of the column. That's why this here, we call it gamma H. Now the bigger the gamma, the stronger the column will be. The smaller the gamma, the weaker it will be in terms of resisting moments. How do we calculate gamma? We just take it from edge down to the center and calculate the distances, as we'll see in the next slide. Here in this slide, it shows gamma equals H times 2 covers, which is this and this, times 2 stirrups, or 2 ties. In this case, we call it a tie. I'm sorry, I'm saying tie. Times, it's minus. Minus 2 covers, minus 2 ties, minus 1 bar diameter, which is half and half. So we went all the way to the center of the bar, center to center of the bar distance. All of this divided by H, that gives gamma. Okay? So curves on the interaction diagram represent rho. 4 dashed line represent the Fs, half F yield, 0 and half F yield, compression controlled limit. We talked about this. And then we have the radial lines, which is the E over H, the ratio of eccentricity to H. And then finally is understanding what gamma is. And gamma is the ratio between reinforcement distance to the overall width of the column.